For the 59th problem on the second ACT practice test, a function f is an odd function if and only if f of minus x is equal to minus f of x for every value of x in the domain of f. One of the functions graphed in the standard xy coordinate plane below is an odd function. Which one is it? So with this problem, it will be useful to know the difference between odd functions and even functions. So we'll first look at essentially the two most classic examples of even and odd functions. So let's start first by looking at an example of an even function. And the most common example is just the function y is equal to x squared. And in general, with even functions, f of x is always equal to f of minus x. So this will make more sense once we actually graph this. So let me draw a quick sketch of what this function looks like. So basically, what this identity is saying is that if we were to pick some random x value, let's say an x value of 2 in this case. So when you put 2 into this function, you get 2 squared, which is 4. So we'd end up with a point up here. So basically, an x value of 2 gives a y value of 4. But what this is saying, and it's true for all even functions, is that if you instead chose the opposite of that x value, so now we're choosing negative 2, this statement is essentially claiming that when you put in this x value of negative 2, you get back the same y value as when you put in positive 2. So putting negative 2 in here, if you square negative 2, that's just negative 2 times negative 2, which is positive 4. So you see that 2 and negative 2 both give you the same y value. And what this essentially means graphically, and is true for all even functions, is that they're symmetric about this y-axis. Or in other words, you essentially have a mirror image on either side of the y-axis. And this is true for all even functions. And you can always check if a function is even if you have the equation for the function, since all you have to do is put in a negative x value and essentially see if you get back the function itself. Since if you put in negative x here, and then you square it, negative x times negative x would just give you a positive x squared. So putting in this negative x value, you would just get back the exact same function. And if that's the case, then you know for sure that this function is even. So this is essentially the main example used to teach even functions. But x to the 4th or x to the 6th, or basically x to any even power, those are all even functions as well. But now that we have even functions covered, let's look at odd functions. And our particular question here is asking about odd functions. Now, the basic rule for odd functions is that if you put in negative x into your function, you get back the opposite of your function. So the most common example for an odd function is y is equal to x to the 3rd power. Since if you were to put in negative x here, so let's say this is our f of x, and you put in negative x anywhere you see this x. So f of minus x would be minus x to the 3rd power. And when you evaluate this, what you end up with is minus x cubed. So putting in f of minus x into our function, we get back the opposite of what we started with, since we started with x cubed and we just got back minus x cubed. So this is essentially the hallmark property of odd functions. But graphically, let me draw a quick sketch of what this would look like. You end up with this particular shape for f of x is equal to x cubed. And what this identity means graphically is that if you were to pick some random x value, and on the graph that gives you some particular y value, then if you were instead to pick the opposite of that x value, so instead you'd pick opposite of x, then that particular y value would be the opposite of the y value you get when you just plug in x. So if that seemed confusing, let me use actual numbers. So let's say we have an x value of 2, and when you plug that into your function, you have 2 cubed, and 2 cubed is 8. So an x value of 2 gives you a y value of 8. Now what this statement is claiming is that if you were instead to put in -2, that you should get back -8. And if you actually put -2 into this function and cube it, you do get back -8. So this right here is the essential defining property of odd functions. Now, the truth about odd functions is that they're symmetric about the origin. So even functions over here are symmetric about this y-axis, but odd functions are symmetric about the origin. So if you were to rotate this positive part 180 degrees about this origin, you get back this curve here. So now that we know the difference between even and odd functions and their properties of symmetry, we can actually answer this question. So one of the functions graphed in the standard xy coordinate plane below is an odd function. Which one is it? So we're looking for symmetry. You can see A and B that you essentially have mirror images on either side of this y-axis. So both A and B you could claim are even functions since they are flipped across this y-axis. So neither of these would be the correct answer. And choice C does not look like it has either symmetry about the y-axis or symmetry about the origin. Since if you were to rotate this 180 degrees, you should see it over here if it was an odd function, but you don't. So this one is neither, and the same could be said about this one since it doesn't have any symmetry to it. And choice letter E actually looks exactly like our example here, and it goes through the origin, and it looks like if you were to take this part of the curve and rotate it about the origin 180 degrees, you would end up with exactly this curve here. So choice E would be our final answer here.